Imagine the world you see around you. It has 3 dimensions. You can move forward and backward, you can move left and right, and you can move up and down. We call this familiar place Euclidean space. It's the space of our everyday experience, the one we navigate without a second thought. To locate anything, like a star in the night sky or a book on your shelf, you just need 3 numbers, its coordinates. This simple intuitive framework has been the bedrock of physics for centuries. From Newton's laws of motion to our understanding of planetary orbits, it's a reliable map for the macroscopic world, the world we can see and touch. Now, let's stretch our imagination. What if space wasn't limited to just 3 dimensions? What if it could have 4, 5, or even an infinite number of them? This is the core idea behind a Hilbert space. It's a generalization of the space we know and love. Think of it as a cosmic playground with an unlimited number of directions to explore. While we can't physically point to these extra dimensions, they exist in a purely mathematical sense. They provide a vast, abstract arena where the strange and wonderful rules of quantum mechanics can play out, far beyond the confines of our 3-dimensional intuition. This abstract space isn't just a mathematical curiosity, it's a necessity. The quantum world is far more complex than our classical one. A single particle, like an electron, possesses properties that can't be neatly described by just its position. It has spin, momentum, and energy, each behaving in ways that defy our everyday logic. To keep track of all this information simultaneously, we need a space with enough room to hold it all. Hilbert space provides that room. Each new dimension corresponds to a possible state or property of the particle, creating an infinitely rich landscape for describing its potential realities. So, a Hilbert space is like an upgraded version of our familiar 3-dimensional space. It shares some fundamental properties, like the ability to measure distances and angles between points, but it expands the concept of dimensionality to an almost limitless degree. This expansion is not just for show, it's the essential mathematical tool that allows physicists to build a coherent and predictive model of the subatomic realm. It's the stage upon which the entire drama of quantum mechanics unfolds. A universe of pure possibility waiting to be observed. In this vast Hilbert space, how do we represent a quantum system, like a single atom or a photon of light? We use something familiar from our own world, a vector. Think of a vector as an arrow. In our 3-dimensional space, an arrow has a length and a direction. It can point from your home to the local shop, for instance. In the quantum world, a state vector is also an arrow, but it doesn't point to a physical location. Instead, it points to a specific state of the system. This arrow encapsulates everything there is to know about that particle at that moment. The direction of this state vector is what truly matters. Imagine our Hilbert space is a giant infinite sphere. The state of our particle is represented by an arrow pointing from the center of the sphere to a specific point on its surface. If the particle is in a definite state, say, an electron with its spin pointing up, its state vector points steadfastly in one particular direction. If its state changes, the arrow swivels to point in a new direction. The entire life story of a quantum particle is simply the journey of its state vector as it moves through this abstract, high-dimensional space. But here's where it gets truly quantum. Unlike an arrow in our world, which can only point one way at a time, a quantum state vector can be a combination of different directions. This is the famous principle of superposition. An electron's spin doesn't have to be just up or down. Its state vector can point somewhere in between, representing a mixture of both possibilities at once. It's as if the particle hasn't made up its mind yet. It exists in a haze of potential outcomes, and the state vector is the mathematical description of that haze. This is why infinite dimensions are so crucial. A simple property like the position of an electron isn't just one value, it could be anywhere. To describe this, we need a dimension for every single possible location it could occupy. Since there are infinitely many points in space, the Hilbert space for a particle's position must have infinite dimensions. This vastness allows us to describe not just simple, discrete properties like spin, but also continuous ones like position and momentum, making Hilbert space the all-encompassing framework for quantum reality. So we have a state, represented by a vector in Hilbert space. How do we get meaningful information out of it? We can't just look at the vector. This is where another key concept comes in, the inner product. The inner product is a mathematical operation that lets us relate two vectors. In essence, it tells us how much one vector projects onto another. Think of it as measuring the shadow one arrow casts upon another. This simple operation is the key to unlocking the probabilities, hidden within the quantum state. In quantum mechanics, the probability of finding a system in a particular state is found by taking the inner product of its current state vector with the vector representing that target state. Let's go back to our electron, in a superposition of spin up and spin down. If we want to know the probability of measuring its spin as up, we take the inner product of its state vector with the up vector. The result of this calculation, when squared, gives us the exact probability. It's a cosmic fortune teller using the geometry of Hilbert space to predict the odds of any given outcome. But what does it mean to measure something in the quantum world? A measurement is not a passive act of observation. It's a powerful operation that fundamentally changes the system. In the language of Hilbert space, physical observables like energy, momentum, or spin are represented by special mathematical objects called operators. An operator acts on a state vector and, in a sense, forces it to make a choice. When we measure the spin of our electron, the spin operator acts on its superposition state vector. This act of measurement is dramatic. The state vector, which was previously pointing in a direction representing a mix of possibilities, is instantly forced to collapse. It snaps into alignment with one of the definite outcome vectors, either up or down. The probability of which way it snaps is determined by the inner product we discussed earlier, but once the measurement is made, the superposition is gone. The particle is now in a definite state. This collapse of the wave function is one of the deepest mysteries of quantum mechanics, and it all happens within the geometric framework of Hilbert space. You might be wondering, why go through all this trouble? Why invent this bizarre, infinitely dimensional space to describe the universe? The answer is simple. It works. Brilliantly. The mathematics of Hilbert space provides a rigorous and stunningly accurate language for describing the subatomic world. Without it, quantum mechanics would be a collection of disconnected observations and paradoxes. Hilbert space provides the unified structure, the grand stage where all the quantum actors, particles, waves, and probabilities can perform their parts in a consistent play. The concept of superposition, which feels so alien to our intuition, becomes natural within this framework. A state vector pointing in a mixed direction is no more mysterious than a diagonal line on a graph. It's simply a combination of the horizontal and vertical axes. Hilbert space allows us to treat these ghostly combinations of states with mathematical precision. This makes it possible to understand and engineer technologies like quantum computers, which harness the power of superposition to perform calculations far beyond the reach of classical machines. The qubits in a quantum computer are nothing more than state vectors being manipulated in their own little Hilbert space. Furthermore, the idea of measurement as an operation that transforms a state provides a clear, albeit strange, picture of the observer effect. It explains why the act of looking at a quantum system changes it. The operator representing our measuring device interacts with the state vector, forcing it out of its delicate superposition and into a single classical reality. This interactionist view, grounded in the geometry of Hilbert space, resolves many of the conceptual hurdles that plagued the early days of quantum theory, turning philosophical quandaries into solvable mathematical problems. In the end, Hilbert space is the backbone of quantum mechanics. It's the invisible architecture that supports the entire theory. It gives us a way to represent quantum states, to calculate probabilities with unerring accuracy, and to model the profound impact of measurement. It takes the weirdness of the quantum world and translates it into the elegant and powerful language of linear algebra. Without this abstract playground, we would have no way to make sense of the fundamental rules that govern our universe. It is, in a very real sense, the true space in which reality unfolds.